The light that we are going to build here is based on this 30 watts RGB LED module, which is widely available from various online sources that deal with electronics parts and components. It consists of 3 rows each of 10 LEDs connected in series, 10 red, 10 green and 10 blue LEDs. The module that I ordered originally had a common anode for all 3 rows of LEDs, which of course has advantages for other applications, but since we are going to power the LEDs with a separate power source for each row, for this project we need to cut and split the anode terminals. I already did that to this module, and here you see it with the soldered wires ready to be mounted and later connected to the power. A few words about how we are going to power the LED module. For those who are not familiar, the relationship between the current and the voltage of an LED is exponential, which means that a small voltage change across the LED terminals will result in a large change of the current. In other words, the current increases very quickly with increasing the voltage, and if we somehow do not control it and limit it externally, it can easily exceed the maximum rating, which can result with overheating and potentially destroying the LED. So, to ensure safe operation, an LED should be driven from a constant current power supply with a current value which is less than the maximum rating for that LED, and proper care should be taken for the heat dissipation. The most convenient and simple way of powering indicator LEDs is to use DC voltage source and serial resistor with a pre-calculated value, but that method would be very inefficient for high power lighting applications due to the high energy loss. A much better and efficient solution for powering the LED modules used for lighting, that can also ensure operation from a wide range of input voltages, is to use DC-DC converters that have both the capability of setting the output voltage and setting a limit to the output current, and that's exactly what I did for this project. Since the common solution is to use 3 identical converters, the highest output voltage needed will determine the specifications of all 3 converters. In our case, the operating voltage needed for the row with the 10 blue LEDs in series is the highest, and it's somewhere at 32 volts. So we'll need a DC-DC converter capable of providing stable output voltage of at least 33 volts. The converters that you see here are step-down DC to DC converters based on the famous XL4015 integrated circuit from XL Semiconductors, and fit perfectly for this project. Going into more details here about the design and how these converters operate would take too much time, and it's a subject for a separate video. But the most important information that you need here is that this is the potentiometer for setting the output voltage, and this is the potentiometer for setting the limit to the output current. The maximum output current that they can supply is much higher than the current at which they will operate in this device, which means that we are in the safe zone and we shouldn't have any issues with overheating. Now a few words about the LED module heat dissipation. The power LEDs are far from being an ideal light source, and most of the consumed electrical energy is converted to heat. Therefore, we'll need to take care for proper heat radiation to prevent overheating of the module. For this project I used several aluminum heat sinks, which I already had available from various defective electronic devices that I keep for this purpose. Of course, we'll also need a thermal paste, which is an inevitable component needed to minimize the thermal resistance between the module and the aluminum radiators. To provide the possibility of powering this light with a wide range of the typically available input voltages, like for example 12 volts from the car battery or 19 volts from a laptop power supply, I also included a boost DC-DC converter to power the LED drivers that you already saw. This converter can accept a wide range of input voltages, it has an input protection with a diode, and it also has a capability of setting the output voltage and setting a limit to the output current. For this circuit I set it to give an output voltage of 35 volts, and I limited the output current to 1 ampere. The reason why I ended up using 3 step-down converters as LED drivers and this step-up converter in addition is because I already had these parts when I started this project. Normally I could have also used just 3 boost converters set to the desired output voltages and have the same functionality with a reduced total cost. Since my initial idea was to put everything in a proper enclosure, which as a consequence can obstruct giving up the heat to the ambient air and increase the possibility of overheating during longer operation, I decided also to include a fan in order to facilitate a faster heat removal. The nominal voltage for this fan is 24 volts DC and the nominal current is 50 milliamps. You can see on the schematic that it is connected to the output of the boost converter through a 360 ohms resistor, as a result of which its operating voltage is reduced to 20 volts. I did this on purpose to lower the RPM value and reduce the noise that it generates during the operation. Other components that we'll need are lens with a lens holder and a reflector that fits to the LED module, one panel mounting switch used as a main device switch, panel mounting fuse holder with a 5 amps fuse, a 5mm yellow indicator LED for power on indication, 3 separate switches for each color, barrel jack adapter, wires, 2 resistors, general purpose connectors of this type, and some heat shrinking tubing. For building the enclosure and for properly fixing everything, we'll also need aluminum profiles, various scrap plastic elements, nuts, bolts, washers, and tie wraps. To find the current voltage characteristics of the module, I used a linear DC power supply and a resistor in series as shown on the drawings that you see now. The current through the LEDs is measured by the ammeter and the voltage across the LEDs is measured with the voltmeter. The LED module was temporarily mounted on a piece of aluminum heatsink. The values that I measured are shown in the tables. This is the table showing the voltage and the current values which I selected to be the operating points of the module. And again, this is the schematic of the component interconnections. Now, after we got familiar with all the parts and the schematic, it's time to start with the build. Please note that making all of the connections, fixing the elements and building the enclosure takes a long time, and that in interest of time not all of the building steps are presented in their entirety. What is important to follow here is the schematic and the interconnections, especially if you are a beginner in electronics, but when it comes to the heatsinks or the enclosure sizes and form, it's possible that you may have a different idea, materials or preference, so I didn't put the exact dimensions of the elements in the video. First, I'm going to mount the LED module to the aluminum heatsink elements. The elements were already adjusted in size and holes were being drilled for the LED module to be mounted and properly fastened. Here's the LED module mounted to the heatsinks and the wires tightened up and ready to be connected to the LED drivers. Here you see the holes that I drilled needed later for mounting the fan and the plastic base on which the LED drivers will be fastened. And here are the LED drivers mounted to the plastic base, all properly set to provide the required output voltages and currents. The procedure for setting the output voltage and the current limit is straightforward, and I'm going to explain it here real quick. Connect the input of the converter to a stabilized DC voltage source set to 35 volts and capable of providing at least several hundreds of milliamps output current. Connect a voltmeter to the output of the converter and using the voltage potentiometer adjust the output voltage so that it's slightly above the operating voltage point of the LED row to be powered, for example 50 mV more. Disconnect the voltmeter and connect 100 ohms 10 watts resistor in series with an ammeter to the output. Depending on the current limiting trimmer position, the current limiting may or may not be active. If the current limiting is not active, the expected current values should be as shown in the table. Now start turning the current limiting trimmer until you reach the position where the output current will be limited to a value of, say, 150 mA. Remove the resistor and connect the LED terminals instead. Readjust the output current to 275 mA. If you have set the DC-DC converters properly, during a normal operation, both the blue and the red LEDs on the converter board should be on, which means that the driver is providing current and the current limiting is active. If both LEDs are on and you hear a sound from the converter, just slowly reduce the output voltage by turning the voltage trimmer until you reach the value where the sound will disappear. At the end, both the blue and the red LEDs on the converter board should be on. Okay, now let's go back to the assembly. Here you see the backplate that will hold the switches, the fuse and the power on indicator LED. To drill the holes properly, I previously drew and printed this template. This is how the fan and the DC-DC converters will be positioned inside. Here you see the fan mounted to the aluminum base, and this is the sled that will hold the boost DC-DC converter. For holding and fixing the lens, I added 4 machine screws going from the back to the front of the heat sinks. This is how the lens and the reflector will be mounted. Now it's time to fix the converters and complete all the electrical connections between the backplate components, the converters and the LED module. I used these tie wraps to fasten the plastic base to the bottom heatsink element. The electrical connections are now completed. Let's do one more visual inspection and then we can connect the light to the power and test it. Everything appears to be as it should. After this initial test, it's also advisable to check again the input and the output voltages of the converters to confirm that they are within the specs. I'll also measure the input current during the various modes of the light operation, so I can calculate the total power consumption. Okay, now it's time to make the enclosure elements. I made these aluminum elements and these plastic side covers. And here you see the enclosure that I got after putting everything together. Now we can put the electronics inside the enclosure. Here you see the holes that I had to drill through the aluminum frame in addition, so I can later easily reach and hold the nuts during the fastening of the front side machine screws. The slit on the side covers should facilitate the air intake from the back side of the enclosure. The fan inside moves the air from the back to the front, and the hot air leaves the enclosure through the slits on the top cover, which are positioned just above the heatsinks. Now enjoy the next few minutes without hearing me talking. What it follows is the mounting of the handle to the top cover, mounting of the bottom rail, which is needed for attaching the light to a tripod, mounting of the lens, and some finishing touches that will hopefully make this light look better. I'll be back for the final testing and demonstration of this RGB LED light. The RGB LED light is finally finished. Now I'm going to put the mount adapter to the bottom rail and attach the light to my tripod so we can see it from different angles. Next, you'll see the light in various modes of operation. I hope that you find this project interesting and that you learned something new from this video. Thank you for watching and goodbye.